Agile athletic, the helicopter defies physics.
Like the Bumblebee, which on paper shouldn't fly, it somehow does.
This is the only machine perfected to take off vertically and hover.
It's the hover that makes the helicopter different.
It can get to places no other machine could dare.
We train for the worst case scenario, and hopefully the worst case scenario doesn't come up very often.
From search and rescue to attack, technology is pushing the helicopter to perfection. To maintain this unique position, it must constantly reinvent itself, and engineers are taking its design even further. Experimenting with new technology, this is the challenge they face as they strive to build the ultimate. This is the EH-101, a state-of-the-art helicopter. It embodies the quantum leaps made in helicopter technology over the last 70 years. It's down to the test pilot to judge the machine and identify problems no one anticipates.
The role of the test pilot is really, he is the link between the engineers, the man who's designed the aircraft, the men who built the aircraft, and what the aircraft actually achieves. So he is the vital link between the airplane itself and the man who imagined it on the ground.
With high-tech avionics, the machine can almost fly itself.
Now turn on the electrics. We're just about ready now to start the rotors, and obviously helicopters don't have ejection seats, so perhaps that's what made most helicopter pilots doubly cautious, check everything over twice.
From the rotor to the engine, the helicopter is intricately designed. And from the avionics to the materials, this complex machine performs incredible feats. It's the rotor that makes the helicopter unique. As the blades rotate, the air passes over them, allowing it to take off and fly.
The helicopter flies by rotating its wings through the air. The rotor blades are exactly the same as a fixed-wing aircraft's wings. The big difference being is that instead of the aircraft being dragged forward by the engines to give you the lift over the wings, we actually rotate the wings to give the speed through the air that gives us the lift.
It took 30 years of failed attempts before the rotor was finally perfected. And a few pioneers ensured that the helicopter would be born. The first major step was in 1923, when a young Spanish pilot, Juan de la Cierva, had a major breakthrough while designing the autogyro. Cierva worked out that rotor blades needed two crucial hinges in order to fly. The founder of the largest helicopter museum in the world knows without this eureka moment, we wouldn't have the helicopter.
Juan de la Cierva was able to invent the flapping hinge and the lead lag hinge. Now those were two hinges which were fundamental in making the autogyro work, because everybody prior to that had problems with the aircraft effectively trying to fall over, or there being too much stress in the system which caused it to fail.
For the first 20 years of its existence, the helicopter was developed by a handful of enthusiasts, aristocrats, and eccentrics. But not for long. 1950, the outbreak of the Korean War. For the first time in its short life, the helicopter was about to prove itself.
The Korean War, the major issue there was getting the injured out and back to the field hospitals as quickly as possible. And it was quickly shown that the helicopter in that situation was, a lifesaver. It certainly started to demonstrate to the Army generals that the helicopter wasn't just a toy, that you could actually do something useful with it.
From Korea to the Cold War, the military now took possession of the helicopter. But they wanted it to do more, to go faster, and to carry more weight. And if this was to happen, it was the rotor system that needed to change.
One of the problems with some of the old-fashioned rotor blades is that they were in essence like a plank. Slightly aerodynamic plank, but nevertheless a plank.
In 1972, a team of young British scientists set about solving this problem. Peter Wilby and Jeff Byam were part of that team, pushing the technology to its limit. But they faced a classic conundrum that affects every helicopter in forward flight. As the air passes over the rotating blades, it speeds half the rotor up and slows the other half down.
This comes back to what we call the advancing blade problem. And in forward flight with a helicopter, you have the advancing blade here and the retreating blade here. And if I'm going in forward flight, then this blade tip is traveling much faster than the retreating blade tip. So you get two sets of problems. This blade is going slowly at high angle of incidence. This blade is going fast at low angle of incidence.
The team knew that the only way to solve this problem was to drastically change the shape of the blade.
In the early 1970s, blades were very, very simple shapes. They were rectangular and they had almost the same cross-sectional geometry all the way along their length. And we knew that in order to make them more effective, we had to change the planform at the tip and we had to make the cross-sectional shape vary along its length.
We could see there were potentially big gains, but of course we had to convince everybody else that there were big gains.
Not everybody believed us at first. The calculation methods we were using weren't totally trustworthy, so you couldn't just point to an analysis and say, believe it. And so we had to do a lot of experiments. We had to degenerate existing blades. We had to take blades that were already on aircraft and make them a little bit worse in different places to try to see which areas were sensitive. So we found ourselves flying an aircraft and putting sandpaper on the leading edge. And the sandpaper was there to destroy some of the aerodynamic benefits. And then you could map which part of the rotor blade actually had to be attacked first in order to make things better.
It took more than 13 years of tests to change the shape of the tip and develop the right material. The wind tunnel test is the only way engineers can verify calculations before going to full scale. Here, Peter and Jeff return to their prototype to compare traditional blades with the new design.
Drives on.
First of all, they test the rectangular blades. By increasing the speed of the wind tunnel, they measure the limit at which the blades can fly.
Speed increasing.
Their aim is to push the speed, to push the envelope.
The control loads are very high now.
So we could say that this is the edge of the envelope for the rectangular blade.
Very much so, yeah.
And it looks like it's 150 knots.
That's about 172 miles an hour. Next up, the revolutionary swept tip blades. How do they fare?
Better take it gently just to make sure we don't have any problems.
Immediately, it's obvious that the swept tip blades are going faster than 150 knots. In fact, the new blades achieve an extra 20 knots. That's about 23 miles faster in the wind tunnel. Of course, tests can only prove so much, and by 1985, it was time for Peter and Jeff to see if their new blades would work on the real thing.
So you just hope there's nothing unforeseen is going to go wrong. You believe you've covered everything, but you never know.
With bated breath, they nervously watched, but they were powerless, and the new blades were now in the hands of the test pilot.
I suppose within only a few hours we were beginning to realise that yes, it had produced the improvements we were looking for. And a year later, in 1986, almost to the day, we went off and actually took the world speed record.
Flying at 249.09 miles per hour. No helicopter has ever flown faster. Better blades meant a new generation of helicopters that could fly faster and carry more. Whether it's lifting victims out of the sea or transporting equipment across difficult terrain, weight has always been a major enemy of the helicopter designer. But they face a dilemma. They must keep weight down, but they must also use material strong enough to withstand impact.
One of the things about the helicopter is you want it to be as light as you possibly can, because effectively you've got to lift all that weight vertically before you fly off. And so throughout its life, people have tried to make the helicopter lighter and lighter.
Early helicopters were made of steel. Then, in the 1970s, designers looked at new materials.
they've been able to use fiberglass and composite materials, which have the advantage that structurally they can be stronger.
The benefit is that plastic offers much more than steel.
The whole thing makes the helicopter lighter, pound for pound, and therefore you can carry more.
While helicopter designers managed to make a lighter superstructure, they still have one enemy to overcome in their quest to build the ultimate. And it's not the enemy you might expect.
3, 2, 1.
It's a hazard even the best pilots can't avoid. Bird strike. A bird can hit a helicopter windshield at more than 200 miles an hour. This is what can happen, and it's what glass designers are constantly battling against. Since the early 1970s, helicopter and plane windshields have been laminated to protect the pilot. Laminating a windshield involves layering glass with plastic. But in the event of bird strike, even laminated glass can shatter and splinters can be deadly. Then, in 1986, engineers came up with a new idea. They used chemicals to toughen glass. They tried molten salts and heated them up to 200 degrees centigrade. They submerged the glass in these salts. The result, glass that is 10 times stronger. This stronger glass is layered with plastic to form a composite windshield.
The benefit of using composite material is that when a bird hits the glass plies can break, but it's the plastic layers bonded to the glass that actually stop the penetration of the bird into the aircraft cockpit area.
But every new design needs to pass a test. All glass engineers know well. The bird strike test.
It's the ultimate test that the aircraft won't be grounded, won't fall out of the sky, and that the crew won't be killed.
This is a 4-pound pheasant, freshly killed and bound together.
The tonnage we got is 4 pounds, and that's the minimum weight we're allowed.
Okay, well, that's reading 4 pounds exactly.
Okay, that's good.
This 70-foot nitrogen gas gun is highly explosive and can fire a bird at more than 300 miles per hour.
We're setting up for the test for the bird impact test on the windshield on this aircraft, and we're just checking that the windshield doesn't fail when the bird hits it at 270 knots.
That's about 310 miles per hour. Here the target is an aeroplane, but the principle is identical. The windshield must stay intact.
We're going to basically charge the bottles up with nitrogen gas, and when we're ready and we're happy with the pressures, we'll actually fire the button. Three, 2, 1.
Does it look?
Well,
oh, it's excellent. That's a good shot.
Doesn't it?
Yeah.
Hit in the middle. Yes.
All plies intact by the looks of things?
It does.
Yeah, it looks good, Roger. Good centre shot. It looks like it was good on position. And I can't see any visible damage. And I think we look, when we look inside, there's no bird penetration, no plies broken, so it's an excellent result.
In modern helicopters, composites have completely replaced steel and glass, making the machine lighter, slicker, and more efficient. Weight is not just an issue for the superstructure. It's also a problem for the helicopter's beating heart, the engine. The golden age of the helicopter engine was the 1950s. One thing happened that would change the helicopter forever.
I think one of the most stunning step forwards in helicopter was the change from piston engines to turbine engines, because that really made a huge difference in terms of power that was available, the weight of the engine, the fact you could much more easily accommodate 1, 2 or 3 engines in an aircraft.
Well, here we have a typical radial piston engine from the 40s, early 50s. Big, bulky, heavy, lots of things to go wrong with it. And then in the mid-50s, along came the turboshaft engine, far smaller, much lighter, much, much simpler, and twice, 3 times as much power.
Turboshaft engines were transforming all vehicles, and now it was the helicopter's turn. 1965, US troops arrive in Vietnam. Immediately, the increase in helicopter engine power was obvious.
If you imagine that the average family saloon has about 100 horsepower and a really fast production car like some Lamborghini may have 300 plus horsepower, these engines are producing 3,750 horsepower. So you can see the sort of quantum leaps in performance that have been required over the years to enable us to fly these machines.
The helicopter is a complex machine, but it has a unique trick up its sleeve. If the engine does fail, it's possible for the pilot to land safely, so long as he practices.
The classic question is what happens when the engine stops? They have this vision of it plummeting out of the sky, not realizing that every pilot is taught how to auto-rotate, which is basically to turn the helicopter into a sycamore seed.
An auto-rotative landing is a controlled descent, whereby the rotors allow the helicopter to freewheel to the ground.
If you can imagine a sycamore seed, it has a small weight on one end and a wing almost, like a rotor blade.
In this practice landing, the pilot is going to temporarily disengage the engine from the rotor.
Captain's crew, stand by for power failure. 3, 2, 1, go.
We don't come down exactly like a sycamore seed in that we don't turn round and round and round.
Watching the speed coming back, we're in auto-rotation.
Because of our balancing systems, and on the Chinook here we have 2 sets of rotor blades.
Quick reactions are essential, and the pilot must neutralise the rotor so it can spin freely.
Engines now not driving the rotors. Descent established. Best range speed, 80 knots.
Like a sycamore seed, the wing rotates round in the airflow and it cushions our impact at the bottom.
Looking out for the landing area. Good speed. Descending. Checking the rad alt. 100 feet to go, flaring. Brace, brace, brace.
At the last moment in this test, the pilot re-engages the engine with the rotor, pulls the nose up to kill speed, and lands safely.
On the ground.
Strides in design have made today's helicopter engine both light and astonishingly powerful. This unique bird can land without the engine, but the weakest link is still the pilot. South Korea 2001. For some unknown reason, the pilot continues to descend, with tragic consequences.
The most common cause of helicopter accidents is still pilot error.
The intensity of the pilot's workload means a lapse in concentration can be fatal. But in the 1990s, electronic engineers began to deal with this problem. With the use of computers, they are taking the pressure off the pilot. The helicopter has one Achilles heel. It's always been exhausting to fly. But the digital revolution that changed the world in the 1990s was about to work wonders on the helicopter.
So I turn the fuel on up here, this computer-controlled engine. So all I do is turn this knob here from off to ground idle.
The digital control of engines has certainly made life a great deal easier for the pilot because he doesn't have to manage the engine in the same way that he used to have to do. It was very much a balancing act in the early days with the relationship between the engine and the rotor because, of course, every time you changed the rotor, you had to change the speed of the engine, and it wasn't automatic. You had to accommodate that yourself as well. With modern engines, with digital control, you set the engines up, they look after themselves, and they provide the power when you want it.
Computers have also transformed the helicopter's guidance in what engineers term avionics. Gone are the mechanical displays. Everything is now electronic, from navigation to night vision. A staggering 1/3 of the cost of the modern helicopter is spent on avionics.
In the early days, and indeed still with some of the simple helicopters today, you're flying manually. So you're still using all your senses to control and fly the helicopter. If you could imagine a ship in distress far out at sea, and a helicopter which has to sort of navigate through a range of mountains to get to it, all that can be done virtually automatically now.
This means that the helicopter can now fly in unforgiving conditions.
We train for the worst case scenario, and hopefully the worst case scenario doesn't come up very often. But when it does, you have to rely almost 100% on the success of the avionics to complete your mission.
December the 18th, 1996, Jamie and his team were called out to a medical emergency on an Irish ferry.
The main avionic which helped us to start with is obviously the radar, to locate the vessel and then to allow us to close and make an automatic transition down to within a quarter of a mile.
20 years ago, without any computer assistance, this manoeuvre would have been high risk, raising the stakes in pilot error. But with avionics, Jamie's pilot could do the job safely.
What the aircraft will do is, flying at 200 feet, all you have to do is press a button and the aircraft will then automatically start to descend and to slow itself. It will then come down to a 50-foot hover without the pilots touching the controls.
With the helicopter now in position, Jamie was able to be winched down to the ferry and recover the victim back to the helicopter.
And the aircraft from its hover will then start to move forward and start to climb away. At the stage it will get up to 200 feet and 90 knots and the autopilot will click off, and at that stage the pilots can take over and fly us back on a route towards the hospital.
Without avionics, search and rescue would be difficult, night flying limited, saving lives treacherous. Advances in technology mean the helicopter can fly day, night, all weather. Operating stealthily, it can almost fly itself. In 70 years, the helicopter has changed beyond recognition, and it'll change again. But in pursuit of making the helicopter faster, there's a danger that designers could undermine its uniqueness.
Each of those steps to go further and faster actually damages the helicopter's ability to hover quite so well. And yet really it's the hover capability which is the essence of the helicopter.
To fly faster, helicopter blades must be broader, but this makes them heavier and less able to hover and to lift.
I think to go faster and yet still be able to hover, you have to add some extra device to a helicopter.
Designers think they may have the answer: the tilt-rotor helicopter.
I think the future is a helicopter that can turn its rotors to become propellers, and therefore it can go much faster and go longer distances than the conventional helicopter.
Helicopter engineers are still striving to build the ultimate. The tilt rotor is already in production. It should be in service with the US Marine Corps by 2006. Civilian tilt rotor helicopters will follow soon after.